Hi everyone and welcome back. This is going to be a short video on the t-distribution and a follow-up to a video I made on hypothesis testing. You'll find the prerequisites for this one in the description box. That being said, let's dive into it. So if you recall what we've seen in the previous videos, the central limit theorem states that regardless of the shape of the distribution of the population under study, be it normal, right skewed, left skewed, exponential, uniform, etc., if we take from that population many samples of size greater than or equal to 30 and calculate the mean of each sample, the probability distribution of these sample means will be approximately normal, allowing us to use the properties of the normal distribution to estimate probabilities or perform statistical tests. But what if we cannot take big samples? We can only take small samples with less than 30 observations. Well, we would have much more uncertainty about the true population parameters, about the true mean and the true standard deviation. And to illustrate this, suppose that our random variable is the height of adult males in a given country expressed in centimeters. And the true population mean is 176 centimeters, while the true standard deviation of the population is 10 centimeters. Now let's pretend that we don't know these parameters, but we take a small sample of size 2, and we get these two heights, 160 and 200. Our sample mean would be 180. Our sample standard deviation would be 28.24. So the sample standard deviation would be almost 3 times higher than the actual sample standard deviation. If we take another sample with heights 160 and 170, the sample mean would be 165 and the sample standard deviation would be 7.07. And if we get the heights 185 and 190, the sample mean would be 187.5 and the sample standard deviation would be 3.53. So our sample mean is more than 10 centimeters greater than the actual population mean, and the sample standard deviation is almost 3 times smaller than the actual population standard deviation. Obviously, if we keep taking samples of size 2, most sample means would still be centered around the mean of the sample means, but we would also have much more outliers. We would have more sample means that are very small and more sample means that are very big. If we compare the t-distribution to the normal distribution, under the t-distribution, the probability of observing sample means that are close to the mean of the sample means is lower, while the probability of observing outliers is higher due to its fatter tails. Of course, the t-distribution remains symmetric, but the percentage of data, the percentage of sample means falling between, let's say, -2 and +2 standard errors from the mean of the sample means is going to be different than the percentage we get with the normal distribution. Remember that with the normal distribution, we have 95.45% of data of sample means falling between -2 and +2 standard errors from the mean of the sample means. But for the t-distribution, it really depends on the sample size. In fact, I should say that it really depends on the degrees of freedom, but since in this case the degrees of freedom are equal to n-1, we can say that it depends on the sample size n. If n is small, the percentage of data, in this case of sample means, falling between -2 and +2 standard errors from the mean of the sample means is going to be much smaller than the percentage we get with the normal distribution. But as sample size increases, this percentage is going to get closer and closer to 95.45%. In other words, as sample size n increases, the t-distribution starts to look more and more like the normal distribution. the fatter tails we have in the beginning when n is small become thinner and thinner as n increases, and its height gets closer and closer to the height of the normal distribution as n increases. Now let's actually calculate this percentage using an online calculator on stattrack.com. So we're going to use the t-distribution calculator. Suppose that our sample size is very small. Suppose that we have a sample with 2 observations. In this case, the degrees of freedom are equal to 1 because it's n minus 1 degrees of freedom, remember. We want to compute the probability or the proportion of data falling between -2 and +2 standard errors from the mean of the sample means. So -2 and +2. We get this percentage. We have 70% of data falling between -2 and +2 standard errors from the mean of the sample means when we use the t-distribution with a sample size of 2 observations, very small sample. Now let's increase our sample size. Let's say that we have a sample size of 30 observations, which gives us 29 degrees of freedom. As you can see, the percentage is now very close to what we get when we use the normal distribution, which is 95.45%. We are 1% below. Let's increase the sample size. Let's use a sample size of 50. We are closer. Let's use a sample size of 100. As you can see, we are getting closer and closer to the percentage we get when we use the normal distribution, which means that as the sample size increases, the t-distribution looks more and more like the normal distribution. One last time, with a sample size of 1000. As you can see, we are now at 95.42%. Instead of the 95.45%. So we are very, very close to the normal distribution. Finally, when should we use the t-distribution instead of the normal distribution? We should use the t-distribution when sigma, the population standard deviation, is unknown, and when a sample size n is less than 30. If we are in the presence of these two conditions, we should use the t-distribution. If sigma is known, so if the standard deviation of the population is known, we should use the normal distribution regardless of sample size. It doesn't matter if your sample size is very small, small or big. As long as sigma is known, we use the normal distribution. That being said, some statisticians say that we should always use the t-distribution whenever sigma is unknown, regardless of sample size, while some statisticians say that it is okay to use the normal distribution when sigma is unknown, as long as the sample size is large enough. And we use the t-distribution when we perform a t-test, where we calculate a t-statistic with n-1 degrees of freedom using this formula. And we use the normal distribution when we perform a z-test, in which we calculate a z-statistic using this formula when sigma is known, and this formula when sigma is unknown. And just to clarify, in these two formulas, x bar represents the sample mean, mu represents the population mean, or the mean of the sample means, if you will. S is the sample standard deviation, n is the sample size. That's the end of this one. If you liked the video, if you deem my content helpful, then please consider subscribing to my channel, sharing this video with people who might be interested in data science. That would help me a lot if you do that. That would help me grow this channel, bring this channel out of the shadows. And I'm still a noob at video editing. I'm still trying to improve the quality of my videos. both in terms of content and audio. So far the audio quality was awful because I was using my laptop built-in microphone. So I bought a new microphone, and I hope that from now on the audio quality will improve. Thanks for watching, especially if you watched the video from beginning to end, and see you in the next one.